Welcome to today's episode of Deconstructing CDK Patterns. And in today's episode, we're not deconstructing one, but we're deconstructing three separate patterns. And the reason why is we're going to be talking everything Lambda. This is about what way do you write your code bases, what way do you deploy your functions, and what do you use Lambda for. So this is something that has been discussed since the day Lambda was invented, and there have been lots of controversial opinions. I'll try not to be too controversial today. So the three patterns that we're going to discuss are the single purpose function, the Fat Lambda, and the Lambda-lith. And if you want to see the code base as we go through this, you can either visit cdkpatterns.com or you can use the command line script in the bottom left, npx cdkp init, the Lambda-trilogy. The scenario we're going to use to demonstrate the differences is that of a serverless calculator. This calculator, it's not a great calculator. It only has three available functions, which are add, subtract, and multiply. And it's going to be hosted behind a web server where it takes two numbers as query params on the URL. Those query params are first num and second num. So you can see that this example URL shows you it would be calculator.com/add, question mark first num equals 3, ampersand second num equals 4, should return us a value of 7. So if we implemented this using the single purpose function pattern, what this would look like is we would have an API gateway that has three named routes, one for add, one for subtract, and one for multiply. Each of those routes would point to an individual Lambda function, which would be an add Lambda, a subtract Lambda, and a multiply Lambda. And each of those Lambda functions would have their own code base. So inside add.ts or pi, you would have the logic that takes those two numbers and adds them together, whilst inside subtract.ts, you would have the logic that takes those two numbers and subtracts them, and inside multiply.ts, you'd have the logic that takes those two numbers and multiplies them together. The benefit of this is that every Lambda is isolated from every other Lambda. Everything is completely independent. This is pretty much serverless in its purest form. So some pros and cons for this is that, first of all, in a pro, this gives you maximum code reusability. You've broken your system down into single responsibility functions. That means you have basically a box of Lego to play with, and you can reposition it in whatever order that you want. It's just a case of orchestration. AWS has a bunch of functionality to do that these days. Secondly, because you've broken your code base down into these single functions, your code is going to be more testable. It's not a case of you need 50 dependencies in order to run one particular function. It's just a function. It just does what it says on the tin. The third pro for this is that if you try to ramp up a new developer on your code base, say somebody joined today and I asked them to modify the add function, it's only something like 7 lines long. So the cognitive burden for getting up to speed to modify that function is pretty low. And then finally, and probably the most important one, it's a lot easier to optimize the cost and execution times of your Lambdas if they're all independent from each other. So what that means is you could have a troublesome Lambda. Say for some reason our add Lambda was taking 327 milliseconds to respond, whilst subtract could do it in 40 milliseconds. You can go into the code base for add and you can say, oh, I'm pulling in this extra dependency here, which is making this library a lot bigger than it needs to be. So I'll just delete that and then deploy a new version and see what happens. You can actually version and interrogate independently without impacting the rest of your application. Now, for the cons of this, because your application is broken down into those Lego blocks, for me, you have to have a fully event-driven architecture for this to work. I just haven't seen anyone do it in any other way. The second con is that in the scenario of our serverless calculator, it's easy because you can picture a calculator in your head. So when you see the single purpose functions, it's easy for you to know how it stitches together. But in a real world app, if there was 700 of these, it would be hard to see the bigger picture of how this is all stitched together if you don't previously know all of that logic in your head. And then finally, system maintenance can be an issue with this as your number of Lambda functions grows. So say all of your functions pull in a particular package, and that particular package releases a security patch which is critical. That means you now have 700 deploys to make. Now, crucially, you can deploy the first one and see how it impacts your codebase and your architecture, and if everything goes well, deploy another 10, and then maybe another 30, and gradually roll it out. So you've got the advantage of, because they're all independent, you can do this sort of partial rollout, but you also have 700 deploys to make. So you need to bear in mind regular security patching grows with your number of functions. And to me, that's pretty much what created the Fat Lambda. So this pattern, it's pretty similar in that we have an API gateway, and on that API gateway, we have 3 named endpoints, add, subtract, and multiply, with 3 distinct lambdas. But the difference here is that we don't have 3 code bases. We don't have add.ts, subtract.ts, and multiply.ts. Instead, it would be called calculator.ts in real life, but we have fatlambda.ts, which contains the 3 methods that are used. So they're all in the one file, and that's okay. But what it does mean is that every lambda has the code included for every other lambda within this bounded context. So that's why it's called the Fat Lambda. Now, the pros and cons of this. Related logic is grouped together. So as I mentioned, you could call your file calculator.ts, and add, subtract, and multiply make complete sense in that context. You as a developer can go to that and go, yep, object-oriented, low coupling, high cohesion, I understand this. So that's a really good point for me with this. The second one is that you can actually share code really easily between lambdas because they're all using the same file. So it just has to be a method in that file and they can call it. And you didn't need to do something like package your code up and deploy it to npm or create a lambda layer. It was just there. And when your lambda gets deployed, you know what version of the code base it's in and what version of that common logic it's using, which is pretty nice. The final one is that this does reduce your security footprint because whereas in the previous example, if there was a security patch needed to be deployed, I had to deploy those 3 lambdas independently. In this one, if I make a change to this file, there's only one package.json, so I update it once, and all 3 of these lambdas will get the update, which is pretty nice. Now, it's not all pros. There are cons. So the first one is how big is too big? Every lambda has the code for every other lambda that's in this file. Now, size is the biggest problem with lambda functions today. The bigger your lambda gets, the slower it will start, the longer it will take to process, the more it will cost. So you really need to be careful with the Fat Lambda as to how much code you group together. But it's something that you can monitor and break out as you need. The second one is you do have an increased blast radius for changes now. Whereas in the first example with the single purpose function, everything is independent from everything else. If you pull in a new version of a library or make a change to a common function, you could take down an entire section of your architecture because it's all in that one file. So it's just something to bear in mind. You've traded developer experience for increased blast radius with this pattern. Finally, we have the Lambda-lith. Now this one is very different from the other 2. We have an API gateway that is used as just a proxy. So any URL that hits this gateway just gets passed straight through to one Lambda function. And inside that Lambda, we deploy a traditional framework like Flask or Express. And inside there, through the routing functionality that framework provides, the traffic gets redirected back to the add, subtract, and multiply methods in that framework. And all this logic lives in one file, lambda-lith.ts. So this one is pretty much treating Lambda like a Docker container. Now, there are pros and cons to this in that because you're using an established web framework, the local developer experience will be brilliant, which is something that I can't really say for the other two. Whilst tools like Serverless Framework and SAM have made running API gateways and running Lambdas locally acceptable, we're still not at the level we were at before serverless. So that is why you pretty much do this pattern, local developer experience. The second one is that because you're using Lambda like a Fargate container or like a Docker container, you could deploy this to Fargate if it gets too big for Lambda with pretty much zero changes. You could probably push it to both places if you really want. And then finally, developers already know these frameworks. So if you're sitting with a Flask service on-prem and you need to get it to the cloud, and it doesn't really matter how quickly it responds and it has a low volume of traffic, perfect pattern. Now, the cons are, is this really what Lambda was built for? Is it what it excels at? If you really think about what you're doing, as I mentioned in the last pattern, the more code you put in a Lambda, the longer the cold start, the slower it gets. So Lambda was designed for small snippets of code that are independent and execute quickly, whereas this is really more like a persistent web server put inside a Lambda. This gives you a higher exposure to cold starts. And the reason why is because the way Lambda scales, if you have a request currently being processed by your Lambda and a second request comes in, it doesn't multi-thread, it just spins up a second Lambda. And that means that because this Lambda has a web framework inside it, it's probably going to take longer to process a request and finish. You're probably going to be doing more logic in there. So you're introducing a risk of cold start issues. The next one is that because you haven't really changed how you're building functionality or taking advantage of AWS, you're at risk of just building the traditional ball of mud again, only this time it's in Lambda, but it's the same thing that we've had for years in many different forms. Next one, so one of the many benefits of serverless is that you don't need to keep versions up to date. With Lambda, it's pretty much like, I want node 12, and then when node 14 comes out, you just update. But that's about it. Whereas by introducing Express and Flask, you need to make sure that you're keeping that dependency up to date. Otherwise, it's a security risk. So you've sort of deserverlessed a Lambda. And then finally, these frameworks don't just run natively inside Lambda, unfortunately. You need an adapter to make them compatible with Lambda and API Gateway. These adapters are not provided by AWS. These are all community driven. So you're really putting yourself at the mercy of the community as to how well these are maintained. If you build a really important application in this way, can you really vouch for how secure that adapter is and how secure it'll be in 8 months? That's something that worries me with that. Now that we have walked through the theory of the three different patterns, let's bring down the code base. So npx cdkp init the Lambda-trilogy. And what this does is it does a shallow clone of the repo and does an npm install and an npm run build. So this is really just a helper function to speed things up. While it's doing the npm install, you can see that we have our Lambda-trilogy codebase. The first thing to point out that this is different to other CDK patterns in the sense of we have 3 CloudFormation templates. Usually we only have 1, but because this is 3 patterns, I decided to use 3 different CDK stacks, and that means that CDK translates to 3 deploys, 3 CloudFormations. So I'll show you that later. But now that this has been brought down, I can just jump into it and run deploy. It takes a while to deploy because there's 3 CloudFormation stacks to go, so I'll leave that running while I talk through the code base. First thing to point out, as I just mentioned, inside the bin file, we have three different stacks, which represent the three different patterns. The single purpose function stack, the Fat Lambda stack, and the Lambda List stack. So this is a pretty cool feature of CDK in that right now it's going to deploy all three of these, but after these are deployed, if I only made a change to, say, the Fat Lambda stack, it would only deploy that one. CDK has logic to work that out, so it's pretty nice. So next thing, I'll work my way in the same order as the presentation, from single purpose function to Fat Lambda to Lambda-lith. If I go into the single purpose function stack, you can see that we have our three lambdas, add, subtract, and multiply. And these lambdas are coming from this lambdas single purpose function folder, which should be here. Add, multiply, subtract. And then each of them have their own file, and they're all pointing to a method called handler in that file. If I jump into the add function, you can see this is, as the name describes, single purpose. It has a handler that takes two query parameters and adds them together and then sends back the response. Now, I don't know if you haven't seen this syntax before. These question marks are optional chaining, which is a new feature of JavaScript. And then the double question mark at the end is nullish coalescence. What this basically means is that the first question marks mean if query string parameters isn't on the event object, just set it to null and carry on. And then the double question marks at the end say if the left-hand side of this is null or empty, set a default value of 0. So that's pretty nice new syntax. The next thing I want to point out in this file is this sendRes method. API Gateway expects the response to be in a very particular format whenever you use a proxy method. So I just use a helper method. It's the easiest thing to do, which just sets the status code and the headers and the body. But in this implementation, you can see that add, multiply, and subtract all have that method because each function is independent of the other ones. Now, I could have went down the route of packaging up sendRes in either an npm package or using a Lambda layer, but for the purpose of this, you can see we have a small amount of duplicated logic in our lambdas, which gives us autonomy. The next thing to point out is our API gateway itself is not a proxy gateway, and it has three endpoints on it: add, subtract, and multiply, which point at our three lambdas, as you expect. So nothing too strange about this pattern. The next one is the Fat Lambda stack. And this one looks very similar to the last one in that we have our add lambda, our subtract lambda, and our multiply lambda. But the difference is, first of all, they're all coming from this lambdas Fat Lambda folder. If I close that one. They all come from this Fat Lambda file, and they all point to different methods in that Fat Lambda file. So if I just open it, you can see now instead of exports.handler, we have exports.add, exports.subtract, and exports.multiply. And these methods are identical to what was in the individual functions. The benefit of this is that the sendRes method is in here once, and all of these independent methods can call it because they're all in the same file. So that shows you the difference between the Fat Lambda and the single purpose function in that we can share some code, and it sort of helps as a developer that I can see these are the functions of the calculator are all here in one place. And if I just jump back to the stack, you can see that there's no difference in how the endpoints are defined. We just have add, subtract, and multiply endpoints integrating with our lambdas. Finally, the most interesting of the bunch, the Lambda-lith stack, which has bare bones architecture. It has a lambda function, and it has a gateway that just says point everything at the Lambda-lith. Our Lambda-lith is inside Lambda-lith, so let's just go there. And the first thing you'll notice is that this is the first lambda that has a package.json. The reason why is because we need these two dependencies. We need to pull in Express and we need to pull in the adapter to allow Express to work with Lambda and API Gateway. The next thing about this, which is pretty nice, we can have a local start command, which I've programmed in here in this package JSON. So it's one of the features of the Lambda-lith. We can actually just start up this Express server locally. Jumping inside the Lambda-lith itself, this is now an Express app, which has an Express router, and the routes are all defined in Express. So anyone who's ever used Express before, this should look pretty familiar to them. This is just standard Express logic. The difference, so it has some of the benefits of the Fat Lambda in that all this logic is in the same file. The difference with this one is at the bottom, where we can actually distinguish between if it's running in a Lambda or if it's starting up locally. And we can say if we're running in a Lambda, use the adapter. Otherwise, just start it up as normal. So to show these functioning, in our CloudFormation stack outputs, we have 3 URLs. This one is the single purpose function. So I'll just show you it. I just copy this, bring it up here. I'll do the add function. First num 4, second num 3. We should get back 7, which we did. You can see over here. If I change the add to subtract, we get back 1. If I change subtract to multiply, we get back 12. So that was the single purpose function. If I scroll up, here's the Lambda-lith. I made it look slightly different, but you'll see in a second. So I just swap out API Gateway URL. I've just hit the Lambda-lith and it has sent us back a result of 12. If I change multiply to add, we get 7. And if I change that to subtract, we get 1. So it works outside of the fact that I sent back a JSON instead of just the number. It works identical to the single purpose function. And then finally, Fat Lambda. I just swap this out. Subtract, we get 1. Add, we get 7. Multiply, we get 12. So you can see it doesn't really make a difference to the end user how these are all organized, but they are 3 very different strategies for how you organize your code. Hopefully you enjoyed this walkthrough, and if so, come follow me on CDK Patterns on Twitter, star the repo on github.com, and hopefully I'll see you again on a future episode of Deconstructing CDK Patterns.